This is an oral presentation on the experiment, the content of phosphoric acid in Coca-Cola, where we do a titration with sodium hydroxide into phosphoric acid to reach two equivalence points. And the goal is to be able to determine whether or not there is phosphoric acid in Coca-Cola, or if there could be other acids in it. The experiment is split up into 3 parts, but all of them are with the titration. And the way we set up the titration was that we took a tripod, where we put a burette on the tripod, which we filled up with sodium hydroxide and zeroed it out, so we were able to tell how much sodium hydrox we had used. Below the burette we put a 100 milliliter beaker, and also a pH meter, which was like connected to the computer, so we could measure the pH value at all time. The beaker was on a magnetic stirrer, so we had a magnet, so it was under stirring all the time. In the first part of the test we did a colorimetric titration. First we used methyl orange, which is an indicator that goes from red and then it goes to yellow when it has reacted. And it measures a pH between 3.3 and 4.4, and that's where it changes color. And there we were able to see that the pH, that the first equivalence point happened at around 7.5 milliliter. And then the other colorimetric test was with phenolphthalein, where it went from clear to pink at around 14 milliliters. Then we started the important experiment, which were the titration of phosphoric acid, 25 milliliters of phosphoric acid. And there it's important to look at the reactions that happens. So we're adding sodium hydroxide to the phosphoric acid, and one of the hydrogens are separated from the phosphoric acid and becomes water. But then we still have the dihydrogen phosphate back, which is an acid too. It's just a weaker acid. Then when all the phosphoric acid has been used, there's another reaction happening, because now we only have dihydrogen phosphate back. So we look at this reaction. It's again sodium hydroxide reacting with the dihydrogen phosphate, and once again the hydrogen is released and becomes water and reacts with the OH minus, the hydroxide ion, to form water. And then again we have a new acid back, and this is actually a weak base, not an acid, it's a weak base, and it's called hydrogen phosphate. And then when all of the dihydrogen phosphate has been used, there's a new reaction, and that's sodium hydroxide reacting with the hydrogen phosphate to form phosphor, which is a salt, and water. And of course sodium is a spectator ion in this reaction and does not play an important part. But it's important to understand that these 3 reactions, they happen after each other, not at the same time, and that's because that this will always be more reactive, the phosphoric acid, than the other ones. So it has to have been, all the phosphoric acid must be gone before the new reaction can happen. When we had finished the titration, the titration we did 0.5 milliliters of sodium hydroxide, and then we measured the pH value at all time. So here you see the y-axis is the pH value, and the x-axis is the amount of sodium hydroxide in milliliters. When we neared in on an endpoint, we would have more data, so we would maybe measure for each tenth of a milliliter instead of only 0.5 milliliters, because we needed more data there. But we're able from this, for the results, to compare Coca-Cola the titration curve and the titration curve of phosphoric acid. So if we start by looking at phosphoric acid, we know that the first equivalence point happened at around 5.8 milliliters. So that's around here. So that's the first reaction that was done, the one with phosphoric acid turning into dihydrogen phosphate. That's at this point. There's not there wasn't more phosphoric acid right here. And then the other equivalence point happened at around 15 milliliters precise, and that's where there's no more dihydrogen phosphate, and it becomes hydrogen phosphate. That reaction happens, and that happened around 50 milliliter. And if we look at the Coca-Cola, because this becomes important later, this is of course the another experiment with the same titration, just with Coca-Cola, degassed Coca-Cola, which is, I will explain later why it's degassed. But it has the first equivalence point is around 6.5, and the other one is around 17 or 16. So it's a little bit higher than the phosphoric acid, and you can also see that the curves are a lot more. It's not as steep, the changes, and that could be because it's not concentrated acid like phosphoric acid is. Okay, so let's look at the calculations, and bear with me. This is not very nice, but I'll keep going, walk you through it. So first we wanted to calculate the concentration of phosphoric acid, and we did that by first calculating the amount of sodium hydroxide used, and that was done by multiplying the concentration with the volume of how much sodium hydroxide we had used at the first equivalence point. So that was 0.1 molar times 5.8 milliliters, which gave us 0.58 millimole. And then from the reaction we know, 2 seconds, here that the sodium hydroxide and the phosphoric acid is reacting 1-to-1. It's the ratio between them. So we were able to say that the amount of phosphoric acid had to be 0.58 millimole as well. So when we wanted to calculate the concentration, we just said the amount of substance over the volume, and we had the result of 0.0232 molar. Then we had to look at the pKa value of the phosphoric acid, which we just read from the graph, which is half the volume of the volume used for the first equivalence point. So that was 5.8 milliliters, so it was 2.4. That's how much we had used at that point, 2.5. And then we wanted to look at the pKa value of phosphoric acid. We wanted to compare with the real pKa value, which is 2.12, which is read from the book. And now we're able to look at the then we can look at the pKa value of dihydrogen phosphate, as that was the other endpoint. And again, we just looked at the graph. You could see that there was used 15 milliliters, so we took half. That's 7.424. Sorry. And then what we did was that we looked at the again, we wanted to compare with the real number, so that's 7.21. So they are very close to each other, the numbers, so it's probably safe to say that something went right in the experiment and the calculations are right. Now we could look at the first, so we looked at the pH value at the first equivalence point and at the second equivalence point, which was 4.56 and 9.06. But we also wanted to calculate it to be completely sure what the pH value were at the time. We did that at the first by saying we had the formula, which is half times the pKa value of the dihydrogen phosphate, because that's what it had become there, minus the logarithm of, where's my arrow? There it is. The logarithm of the concentration of dihydrogen phosphate. So first we had to calculate the concentration of the dihydrogen phosphate. We did that by again saying the amount of dihydrogen phosphate over the volume, but we had to remember that at this time we're at the first equivalent point and we've added 5.8 milliliters. So we had to divide by that volume, which gave us 0.0188 molar. Then we just used this formula, the pKa value we looked at from the book, and it was where is it? There, 7.21. Yeah, 7.21. And yeah, and then we got the answer 4.47 pH, which is almost the same as what we read from the graph, so it's very unlikely. When we had to do it for the second equivalence point, of course the concentration had changed again. This time we've used 15 milliliters at that point, at the second endpoint. So once again it gave us a new concentration of the hydrogen phosphate, which was 0.015145 molar. Now this time we used not the same formula, because as I told you earlier, hydrogen phosphate is a weak base and not an acid. So there's another formula, which is a half times the pH B value for the base and not the acid, which has a value of 6.79 for hydrogen phosphate. And then we minus that with the logarithm of the concentration of hydrogen phosphate, which was 0.015145 molar. This gave us the answer, and and then that gave us the pH, but we had to minus it with 14 first. And we got the answer 9.69 pH, which is also fairly close to what we had read from the graph, so it's likely to be true. Yeah, so from these experiments and from the numbers being so close to each other, we're able to conclude that the phosphoric acid is present in Coca-Cola, and that it's a part of Coca. Like it's the acidity of Coca-Cola it's likely the phosphoric acid. We also had to consider, and that's what I wanted to return to, that carbon dioxide is acidic too. So that's why we degassed the Coca-Cola, and we did that with this. It's like water goes out here and it creates a what's it called, a pressure, and the air gets out, and yeah, it degasses the Coca-Cola. So it was a flat Coke, so that we could be sure that it was only phosphoric acid we were testing.